Hello and welcome to Chapter 3 of the Solomon's book. We're going to be talking about acids and bases in this chapter. And so the first classification we're going to have is the Bronstead-Lowry definition, and this one is where we're moving around H+. So that was specifically for hydrogens. And so you can think of this as you have a base. So that if you think of hydroxide as the simplest case, you have an acid of HCl. It's got an extra H. The base comes in and grabs it to form your conjugate acid here. So if it conjugate acid, and then Cl minus, your conjugate base. And so this thing is grabbing the hydrogen, ripping it away to make this, and leaving behind the electrons. Okay, so if you are a base over here, when you come over here, you're going to be the conjugate acid. So you're going to be the conjugate acid. When you're at the acid on this side, the corresponding, after you've lost the hydrogen, you're going to be left with a minus charge, stuff like that. So a conjugate, or you're going to lose an H+. You're going to be the conjugate base, and it's kind of so if you're an acid, you're the conjugate base, and the other side base, conjugate acid. In some ways, there's just to confuse you, but what's really happening is what they're saying is if this reaction were going to reverse, this would come in and grab that, so this would act like a base, and that would act like an acid. So in the reverse reaction, how are these things going to interact? Stuff like that, but it's still a little bit screwy on the naming. Stuff like that. So one of the things that happens is if you're running these things in water, basically it's going to be the water itself that's probably going to be doing most of the interactions, because it's going to, because water is a weak acid and a weak base, it can act as both. It's really what you can do is if you have a strong acid or strong base, it's going to react with the water first, and then for that it's going to react. So if you're running in water, it's pretty much going to be OH minus and hydronium H3O plus, something like that you're actually working with. Okay, stuff like that. And so if you have acid and salt and OH minus, and so if it's sodium hydroxide, and this is HCl, aqueous HCl, this is actually what you've got. The sodium chloride is just there they're just there for spectator ions. They're just there to deal with charge. They don't do anything. And so really what's happening is you have the hydronium plus hydroxide making two waters. So that's really what's going on in water. Stuff like that. So stuff like that. And so we can write this, so we can represent how these atoms, how these electrons are moving around. And so what we can do is we can do what's called a curved arrow mechanism. These are going to be important on down the road, but it's there to illustrate, to sort of visualize what's going on here. So with the curved arrow mechanisms, you're going from the electrons, you're showing how the electrons flow. So it's almost always going to be from like a lone pair to where like a positive charge, or a bond to a positive charge. It's always going to be electrons moving to something, so it's negative to positive. Okay, in theory, and you can say you never use them to show the movement of electrons or movement of atoms, since what's happening is the atoms are flowing with the electrons, stuff like that. But it's a habit people get into, so I'm not going to be too big of a stickler in it, stuff like that. But you have to make sure that that the structures that you make don't violate the octet rules. If you're going to be trying to put in that fifth bond into that carbon, you sure as heck be able to. The carbon isn't going to like it, so it's going to have to get rid of a bond. So with that, you can't have more than 4, right? So you can have 3, you can have 2, you can have 4, but it can't have 5. So so if it's going to get that fifth bond made, it needs to break one before you can make the new one. Okay, and so what's going to happen is it's always going to be, so if you have just something like this, H plus, OH minus, right? So these lone pairs are going to be attracted to that hydrogen, so with that, and so these electrons, right? So for that, we only need one bond to hydrogen. It only needs 2 electrons, so those are going to go here. And ours has a lone pair here, and so you're going to make HOH, right? So these 2 electrons are going to turn into this new set of lone pairs, and HOH is going to go here. So in this course, in the organic chemistry courses, you don't think of water as H2O. Think of it as HOH. It makes things a lot simpler to think about. You can also have water acting as a base. It comes in here. But again, these lone pairs are going to be making a new bond to that hydrogen. This hydrogen only needs 1 bond, so we can push those electrons up onto the oxygen. We've already kind of seen that a little bit with resonance structures, but this is working between molecules. Same thing here. OH minus comes in, grabs a hydrogen, pushes those up. Okay, and so and that's all this is. Okay, with acids and bases. Now, Gilbert Lewis came in here. He's the guy that also did the Lewis structures. He came in and said, okay, what if we expanded this beyond H plus? Okay, pretty much anything that can accept electrons, that's going to be an acid. Okay, so that's exactly what's going on here, right? This hydrogen is accepting electrons from something else, right? So it's moving here, and in doing that, it's got to push those away. So it expands beyond that. Pretty much anything with a lone pair can act as a Lewis base, right? We can make a new bond, stuff like that. And so the classic one is Br bromine. So that's got lots of lone pairs here. You got iron, doesn't have its octet filled, right? So that only has 3 bonds, stuff like that. And so this bromine can come in here and make a new bond with this lone pair. And so now everybody's got their octet filled. Now they do have formal charges, but that's for another issue. But now they've got their octet filled. So this is going to be a Lewis acid. This is going to be a Lewis base. This has the lone pairs. So so there are lone pairs here, stuff like that. But we're talking between one molecule to another. Okay? So for this one here, opposites attracts, negatives attack positives, right? So we have negative, right? The negative electrons are going to be attacking the positive side on here. They're going to be on this polar covalent bond. I mean, attracted that H, right? You're going to push those electrons up onto that chlorine. Same thing here, right? So this is a Bronstead case, right? This is a Lewis case, right? So with that, but still, it's the same thing. It's the lone pair on the ammonia coming in and attacking the thing that has the positive charge. So with that, to make a new bond. That's all this is. Okay, so for when we're dealing with carbons, we call these carbocations, carbanions. So you can take carboanions, but these are squish it a little bit more into making carbanions. So it's a carbon cation, so it's a carbocation. It's a carb, so carbon anion. Anions are negative charges. So here, the carbocation, it has positive charge. It's lacking electrons, right? So typically what's happening is it has 3 bonds. It wants that 4th one. Here with the carbanion, it has 3 bonds, but it has its octet filled, but it does so with a lone pair. It doesn't really like to have that. Has a negative overall formal charge onto it, so it's not particularly happy. Stuff like that. And so for here, rich, you can think of it as rich attacks the poor. So for that, a negative charge comes in and attacks the positive charge. So lone pairs come in and attack the positive. Negative attacking positive. That's all this is. Okay, so we actually have terms for these. So, and it's a little bit sort of, you have to sort of, do somersaults to think about this, but things that have positive charges are called electrophiles. They are electron loving. Okay, so what things love negative charges? Well, then, if you love negative charges, what must you be? You must be positive charge, right? So this is an electrophile. It's loving. It wants to be loving on some negative charge. Okay. Conversely, if you're a nucleophile, that means you're nuclear loving, right? So what charge is in the nucleus? It's positive charge. So if you're loving some positive charge, you must be negative, right? So your Lewis base is your nucleophile. That's going to be doing the attacking, okay? Because this thing loves positive charges. There you go. So with that, so for acid-base strength, right? So with that, and so we're going to be using nucleophile, electrophile quite a bit in this course. So with that, so so you'll see this come up a lot. Stuff like that. So for acid-base strength, I'm not gonna have you calculate anything, but just realize just where the pH and pKa comes from. So if you have this little p, it's the negative log of whatever this is. Stuff like that. So you have the equilibrium constant here. So it's products over reactants, but water is a solvent, so you don't have to worry about that. That's not going to change. Stuff like that. And so the negative log of this is going to get your pKa. We do negative, and so that we don't have to deal with. We do the log because we don't like dealing with really small numbers. It's hard to see. But here, this is much more reasonable numbers to think about. We'd rather think of negative 1.3 as opposed to 5.0 times 10 to the minus 2. Stuff like that. Dealing with all those the scientific notation and that kind of stuff. But one of the things you have to remember is the fact that what is it? The each value, when going from 1 to 2, that's not just doubling. It is actually going up tenfold because it's log base 10. And we stick a negative in front of here because most of those numbers are going to be actually positive. This one happens to be super strong, so it's negative. But most of them, you're dealing with small positive numbers, stuff like that. And so if you come along here, right, so as the number gets smaller and smaller and smaller, what's happening is that means it's more acidic. So that means the corresponding base, so the stronger the acid, the weaker the conjugate base. Okay, the more likely it wants to just get rid of it, stuff like that. And so HCl is a very strong acid, it's -7. So that the chloride ion is very, very, very weak conjugate base, stuff like that. But water, right? So with that, so that's a really weak acid, but the conjugate base, the hydroxide, right? That's a classic base, and it's a pretty strong base, stuff like that. And so the weak acid, strong base, strong acid, weak base. So it goes back and forth. Okay, and so you can think about these as the negative. How you can think about the basicity from pKa chart of saying, okay, so if this is its H form, it's hot, the HCl here is going to be -7. Having the H here, it would be 4.7. The HOH here, this is 17. So that means as these numbers get higher, that means that this base gets stronger. The base form of it gets stronger. Okay. So you can use this to predict reactions, because what you want to do is you check the acid on this side and you check the conjugate acid on this side, and what you want is that pKa number to go up. No matter what it is, it's going from 4, from here to 4 to 15, it's going up, you're good. The reaction is going to want to go that one, so go towards the higher numbered side. Okay, and so if we're looking at this, so if we're going from 25 to 35, so 25 to 35, it's going to want to go on the higher side. So that means the reaction is going to go forward. Here we're going from 2 to 4, right? So for that, again, the higher number side is going to be the 4. It's going to be on this side, so it's going to want to go forward. Even though it's smaller numbers, it doesn't matter. You want it to go up. So here it's 12 to 10. So with that, so the number's going down. So really the reaction wants to go in reverse. That's all it's saying. It wants to go towards the higher number side, and it's all relative. Okay, so so another way that you can do this, so when we're dealing with acids and bases, you see this all the time in pharmaceuticals and things like that. If you want to make something in other compounds, if you want to make it more water-soluble, you actually give it a charge. You actually start inducing these ion-ion interactions, right, to make it more soluble. So you can take benzoic acid, it's not soluble, you put in a little bit of base, it deprotonates that, so for that, so it rips the proton off, and so now you got benzoate here, so with that's highly charged. So voila, it's water soluble. So with that, so you can also do this to the other one. If you have an amine, if you have a base on there, you can add HCl, stuff like that, and it makes it the hydrochloride salt. You induce an ion-ion interaction, and so therefore it becomes more water soluble. So the classic example is powder cocaine versus crack cocaine. Powder cocaine is a hydrochloride salt, and so this is soluble in water. And so the way that they go from here to here is they add in a little bit of base, and they neutralize the HCl. That's they rip this off, makes this here. So now you don't have that ion interaction. It's not soluble in water anymore, and then it floats to the top, and you can skim it off. Stuff like that. So this is used quite a bit in pharmaceuticals. So if you see it's some sort of drug HCl, what's happened is they've dissolved it in a little bit of hydrochloric acid, so that's more water soluble, among other reasons. So with that, so you can predict the acidity of something, and so the lower the pKa of that bond, the weaker the bond is, and more easily broken. So with that, so HF is a fairly strong bond, but HI is not. So with that, that reflects in the pKa, and the trend's going down. Okay, so with that, so you can also go as you go across. So CH, NH, OH, F, FH as you're going across. If you look at this going across, it's going to be more acidic. As you go down the periodic table, again, it's going to be more acidic. Where you really want to be, one of the weakest bonds here is going to be this HI. So that's a bond here. So the first thing you're going to want to do is take a look at, if you're looking at SH versus OH here, is you're going to look at this versus this. This SH is closer on the periodic table to iodine than OH, right? So SHOH. So this is going to be more acidic. More acidic. Okay. So with that, so you can also look at the hybridization. So SP So this carbon is sp. So the more s character it is, the more acidic it is. So this is this sp. That means it's 50% s. This one here is sp2. So it's actually only 33% s. This one is 25% s. So this is much more acidic than this. Stuff like that. So you can also have what are called inductive effects. And so if you have the things that are electronegative, stuff like that. So fluorine is more electronegative to this, and so this is going to be again more acidic. This is going to be more acidic. Now, don't get this confused with what I was doing up here. Here we're dealing with just this specific atom that the H is on. Okay, so about that, and so this one you want to be near iodine, right? Because HI is a lot more acidic than HF. Okay, but when you're talking about inductive effects, you're just looking at electronegativity. The normal sort of closer to iodine, the more acidic, or the closer it is to fluorine, the more inductive it is, the more acidic it's going to be. So, having a fluorine in here increases the acidity. More electronegative, so with that, again, it's going to be more acidic. The more you have, more, so if you have one fluorine, it's this, it's 2.6. If you have 3 fluorines, it's going to be negative 0.3. So it's going to be 100 times or 1,000 times more acidic, or I guess 100 times more acidic. So like that. So here, but that effect wears off quickly as you move away. And so the farther you get away, the more, so that the farther away, the less the effect. Okay, so that the other thing is, remember we talked about this, having a double bond right next to your acidic hydrogen makes it more acidic. So about that, so that's why C double bond O's are a lot more acidic than OHs. So about that, so the reason for that is because you have a resonance structure that the molecule can use to stabilize this. So if it leaves, it's okay, and so it's more likely to happen. There's no resonance stabilization with the alcohol if this oxygen here is the only thing that bears that negative charge. So here, both of these oxygens can bear the charge, right? So so if you think about it, weights, right? So this is the only atom carrying that 100-pound weight. Here, so it's going to be really heavy. Here, each one of these is carrying it. So with that, so each of them is really only carrying 50 pounds of weight. It's much more doable because you have this resonance stabilization. It's more likely to happen. Stuff like that. So you also have inductive effects, right? So with that, because you're putting an electronegative oxygen here, so you're going to be pulling that along, stuff like that. So weakening this bond. You don't have nearly as many you don't have those inductive effects here. So again, with phenols, stuff like that. So as opposed to alcohols here, again, you have a double bond hanging right off next to that OH. That makes it a lot more acidic because again, you've got this resonance structure that can stabilize it. So losing that hydrogen is not that big of a deal, so it's more likely to happen. Okay, solvent effects, stuff like that. So polar solvents can increase acidity because it can stabilize the resulting charges. If you try to throw something into a very hydrophobic, so an oil, stuff like that, salt into an oil, it's not going to dissolve, and therefore, like the acid is not going to dissociate, stuff like that. And so, but if you throw it in water, it will, stuff like that. So the solvent can help out. Okay, so like that. So things that have lone, so organic molecules can act as bases. They're going to have lone pairs. They can come in here and rip off hydrogens. So they can make a bond to that hydrogen. These electrons can come up here, just like any other OH. Okay, so like that. So they work the same way, right? So like that. So you have a negative charge here attacking the polar covalent bond here. This H here, so it's going to go there. Okay, and so what's going on here? The negative attacking the positive to go here to make this, and now this can go away to go here, and this can come. Right, there's this chlorine that's going to be hanging around here. That can come and attack. This negative attacks the positive. So it's negative to positive. This ripping away. This is what's called a leaving group. To leave the positive charge behind, and now this negative attacks that positive. So it's always negative attacking positive. Stuff like that. So stuff like that. But remember, so if you need to have a base stronger than water, what you really need to do is pick your solvent much more carefully. So if you need a really strong base, so this is like pKa of like 40 or something like that. In base, all this is going to do is if you put this in water, it's just going to rip off a hydrogen here, and you're going to be left with the OH minus. But if you run it in ammonia, which is, it's going to be able to use its full strength to be able to use this for the O minus, right? So with that, so you can, again, you're going to be able to use the full strength. So you need to get away from water if you want to be able to use stronger acids, stronger bases. So with that same thing here, right? So we're going to be using this a lot down the road with a fairly strong strong base. Here, you can actually rip off that hydrogen to make yourself a carbon nucleophile. So this is going to be important down the road. So be aware. Stuff like that. So you can also use this to use what are called deuterium and tritium labeling. So these are heavy isotopes of hydrogen. So by that, and so what you can do is you can react these, something a base with either D2O or T2O. So with that, and so they act like a base. They rip this away, and so what you end up doing is you end up putting a deuterium on here, and so you can individually label a hydrogen. I'm not going to show you and test you on this now, but just realize that this is a way that you can do it. Okay. Good luck.